Good morning, this is CS4249, Phenomenon and Theories of HCI. This is week 8, in which I'll review and capstone all of the presentations made by student teams over the last few weeks. We will be doing this again later on in week 10. So I'm going to be using this lady in red as an example to go through all of the various topics that we have covered over the last few weeks. Let's start by reviewing what we mean by phenomenon and theories. These are actually the foundations of what we're studying in class as the core part of the achievements that we're looking to do. In specific, we know that HCI design requires understanding both computers, but in a very key and core manner, humans as well. And the student presentations that we have had already and will continue to have in week 9 are basically presenting the component theories of HCI. Not all of them, but quite a few that are salient that you should know as part of this undergraduate course. And as I said, this week and in week 10, we'll be bringing all of these theories together so we'll better understand what we've presented ourselves. So when we think about phenomenon, basically we're asking the question of how do people do a particular activity? How do people do X? It's very much related to the ethnographic studies and the need finding that we've talked about in earlier lectures. And what observations can we make about people? The answer to this question will help us form theories, right? And these are the explanations for the type of phenomenon we see. And surprisingly, in HCI, especially on the psychological level, there are very little agreement than we might expect. We might expect that we have a very good understanding about how people behave, but actually that's not very much the case. We do know from psychology, cognitive science, and ergonomics some basic ideas that we are trying to give you a taste of so that you can leverage them in your own design. Right? And taking phenomenon and theories into considerations leads us into guidelines, frameworks, and encoded heuristics that help us with usability and higher level requirements for any computer system. And we might title this as human factors, right? The idea that we have to study humans if we are to design a system that involves both humans and computers together. In other words, HCI in general. Okay, so what we're going to be doing today is breaking up this lecture into a couple different parts. We're first going to be talking about memory as part of human information processing. And after that, we're going to be looking at attention and other capabilities that humans have. After that, we're going to be reviewing week 7, which is where we covered cognitive models. And then in week 10, we're going to be covering social, emotional, and affective factors. And finally, navigation and wayfinding. There are some goals of the theories that we come up with as part of HCI. And this is most well illustrated by our own students who looked at GOMS and KLM. We'll be going over that a little bit later when we look at cognitive factors. Cognitive models. So on this slide, you can see that GOMS is both a predictive, a descriptive, and a prescriptive model. And so actually, when we think about theories for HCI, there are actually 4 different ways that we can think of it. Descriptive, meaning can we understand and characterize what the phenomenon are when we observe people interacting with computer systems. Explanatory, that tells us why people or why certain phenomenon exist. Prescriptive, telling us how we might go about dealing with designing a computer system to optimally cater for human capabilities. Right? These are the guidelines that you see very often in usability checklists and heuristic evaluation. And finally, predictive. Given a particular human computer system, can we predict how well it's going to function, whether it can cater for the types of errors that people make, and how long it might take to execute a certain task. So that's all the high-level goals for this lecture and lecture 10. And basically, when we look at it at the high level, we're going to be covering all of these different parts. At the top, from the 12 o'clock position, going to go through human processing and abilities, then go to cognitive models for this week, the first two quadrants. Okay, and then we'll be reviewing the rest of these other parts in later lectures. You can notice that they're not completely finished at this step. Okay, so we're going to go into our first very large chunk of today's lecture, which is on human processing and abilities. And in the student lectures that we've seen in week 6, we've had selective attention, Fitts law, and keystroke level models as things that we've covered already. And the first thing we're going to look at is memory and attention. So we know that models of memory are actually very interesting. They are three basic laws that we know that memory of humans is not. And the first one is listed on the slide. It's not a simple information store as we might think of a hard drive or a flash drive, right? It's not just a single store. We generally agree that there are some divisions within memory, right? And our team that talked about levels of processing and 7 stages of action alluded to the memory models that people have talked about. Okay, so even though levels of processing isn't specifically about memory structure, it does point to the fact that it's based on the Atkinson and Shiffrin memory model. Okay, and this was one of the first memory models of humans that proposed more than 2 divisions between short-term and long-term memory. Okay, so they had proposed that human memory has at least 3 stages that they were able to observe from looking at how people perform tasks. So for example, in this slide, we see that there's a sensory store and long-term memory and short-term memory. Okay, and then there's a stage of rehearsal where we take sensory stored information, that means things that we can see or hear from our ears or eyes, and store them in the short-term memory through rehearsal. Okay, when we take short-term memory and we make it into long-term memory, in fact the slide is not correct, it's not called rehearsal, it's called encoding, and we'll talk about that a little bit later. Okay, so we're going to go over this in much more detail. Secondly, memory is not a passive repository. The active use of memory changes its structure. And third, and not least, it's not affected by the type of material to be stored. If we try to store the material or encode it into our long-term memory by mulling about it in more ways, it may become easier to retrieve. So we've already gone through the 3 stages of memory that we saw on the student slides, right? We have sensory stores, iconic, which is our visual memory, and echoic, which is our audio memory. Okay, at least we know that these 2 forms of sensory stores exist. Then we have short-term or working memory, which is where most of our time is spent, thinking about and cognating on what's happening now. And we have our long-term memory store, which stores other information. And we're going to talk about the short-term and long-term memory in more detail. In fact, our short-term or working memory is stored in the prefrontal cortex of our brain. And that's very important because a lot of higher mammals have this part of the brain, and many lower animals do not. So for example, goldfish are supposed to only have 3 seconds of entire memory. That means every 3 seconds they've forgotten everything that's happened before. That's certainly not the case with humans, as we have a working memory that keeps information in store. Okay, so once we process information from our sensory stores, that means from our eyes and ears, it gets passed into working memory. And basically, there are 3 parts of working memory that are important to note. One is in the center, the central executive, and we don't know much about this module. It's just that we know that it helps us assign processing of our working memory into 2 component parts. either one that deals with verbal information on the left-hand side, that's our articulatory loop, as well as the right-hand side, which is our visual spatial sketchpad. That tells us a lot more about navigation and vision. Okay. In our auditory loop, basically we have the capability to store information about what we've actually heard from our sensory store. And we have to keep this information in memory by repeating it to ourselves. So for example, if you're told a phone number and you're rushing to get to a sheet of paper to write it down, to externalize it, then we might repeat it to ourselves. And we can store about 2 seconds of working memory in our articulatory loop. And by repeating it to ourselves in our inner voice, we can help to retain that information into working memory. Okay? And then the visual spatial sketchpad on the right is akin to the same thing, but for vision and spatial reasoning. So we have an inner eye, remembering what we've just seen. So for example, what color was the person wearing that just passed us by? Okay? And basically, when we have working memory, we can use rehearsal, which is discussed on the top left part of the slide, to keep things in short-term memory. For example, if we use our inner voice or our inner eye to rehearse and try to remember what we've just seen or heard, that can keep our information in working memory. But if we don't think about it hard enough, then it decays out of working memory, or if other things exert more priority, let's say another person comes in wearing a very bright colored shirt or there's a loud bang, it can help displace what we have in our working memory, and that information can be lost. Okay, so there's a tutorial that you can look at on YouTube. You can search for the words working memory model, revision tutorial, and then go through more detail if you'd like. But I'd like to end this part by talking about Stroop's effect. This is a 1935 effect that ties working memory with attention. Okay, but before we get there, let's talk about one famous fact that probably many of you have heard about, which is George Miller's 7 plus or minus 2. This says that we can keep up to 7 pieces plus or minus 2 items in working memory. So if you can, at any one point in time, recall 5 to 9 different facts, okay? And this is most often used to justify lots of different types of design decisions made by human-computer interaction designers. For example, perhaps you want to choose only up to 7 menu items, okay, on a screen so that people can decide between them. Okay, this is actually not very well applied by HCL designers. For example, the example that I just gave you is not true because, in fact, when you keep menu items on a page, for example, on a web page, it's easy to rescan them, just visually scan. So it's not true that we only should use 7 items plus or minus 2 here, because we can use our sensory stores to regain information that might be lost from working memory. Okay, so 7 plus or minus 2 has to deal with things that you need to keep inside your head that you cannot use sensory stores to keep. Okay, for example, if you're told a list of 20 words, maybe you're only going to recall 7 plus or minus 2 of them. Secondly, there's been some recent evidence in 2002 that today's generation of people don't practice memory as much, and therefore the number of 7 plus or minus 2 has decayed a bit to about 4 plus or minus 1. So we can keep in today's generation maybe about 3 to 5 items in working memory. Now I ask you to think about why. Okay, so let's take a look at Stroop's 1935 effect now. So wasn't that interesting? That was the Stroop effect, which shows that the visual spatial sketchpad and the articulatory loop can conflict with each other. When we saw the words but they were in different colors than we expected it, the articulatory loop and the visual spatial sketchpad have conflicting information, which is overwhelming our working memory and makes it more difficult for us to pronounce the words as seen. Now we're going to spend some time to talk about long-term memory, which is divided into these 4 parts as we've discussed before. And long-term memory is stored in different parts of our brain. In this green part of our brain, or the temporal lobe, we store declarative memory, or information about facts. Non-declarative memory, implicit memory, which includes information about procedures, like how to ride a bicycle or how to type, is stored in a different part of our brain. For example, when this lady in red bumps into this person who she thinks she recognizes, she is using one part of her long-term memory stored, the recognition of people's faces. But then trying to place where that person comes from evokes a different part of our memory long-term structure. And therefore it's not uncommon that we might not be able to place them because that information is in a different part of our brain. Now it's important to recognize that the synthesis of proteins in our brains allows our neurons to form the new pathways that encode our long-term memory. This process is called encoding or storage. And then subsequently, when we try to recall that information, this process is called retrieval. And it's important to note, as we talked about earlier, depending on the type of memory that we're trying to store, it can be more difficult or more easy to recall. And we can influence this process by actively thinking or elaborating on the information that we'd like to store and trying to make analogies to other things to make it easier to retrieve. This can affect the effectiveness of the retrieving process. So now we're going to watch part of a TED video that you can also watch on YouTube. This is Joshua Foer's Feats of Memory Anyone Can Do. And in particular, I'd like you to listen for Joshua's description of distributed and external cognition, although he doesn't call it that. And to also listen to why he thinks that Miller's number, that's the 7 plus or minus 2, is changing. Again, he doesn't explicitly say this, but it's very important for you to think about why that's the case.
I want to tell you about a very bizarre contest that is held every spring in New York City. It's called the United States Memory Championship. And I had gone to cover this contest a few years back as a science journalist, expecting, I guess, that this was going to be like the Super Bowl of savants. This was a bunch of guys and a few ladies, widely varying in both age and hygienic upkeep. They were memorizing hundreds of random numbers, looking at them just once. They were memorizing the names of dozens and dozens and dozens of strangers. They were memorizing entire poems in just a few minutes. They were competing to see who could memorize the order of a shuffled pack of playing cards fastest. And I was like, this is unbelievable. These people must be freaks of nature. And I started talking to a few of the competitors. This is a guy called Ed Cook, who had come over from England, where he had one of the best trained memories. And I said to him, Ed, when did you realize that you were a savant? And Ed was like, I'm not a savant. In fact, I have just an average memory. Everybody who competes in this contest will tell you that they have just an average memory. We've all trained ourselves to perform these utterly miraculous feats of memory. Over the last few millennia, we've invented a series of technologies, from the alphabet to the scroll, the codex, the printing press, photography, the computer, the smartphone, that have made it progressively easier and easier for us to externalize our memories, for us to essentially outsource this fundamental human capacity. These technologies have made our modern world possible, but they've also changed us. They've changed us culturally, and I would argue that they've changed us cognitively. Having little need to remember anymore, it sometimes seems like we've forgotten how. One of the last places on Earth where you still find people passionate about this idea of a trained, disciplined, cultivated memory is at this totally singular memory contest. It's actually not that singular. There are contests held all over the world. And I was fascinated. I wanted to know, how do these guys do it? A few years back, a group of researchers at University College London brought a bunch of memory champions into the lab. They wanted to know, do these guys have brains that are somehow structurally, anatomically different from the rest of ours? The answer was no. Are they smarter than the rest of us? They gave them a bunch of cognitive tests, and the answer was not really. There was, however, one really interesting and telling difference between the brains of the memory champions and the control subjects that they were comparing them to. When they put these guys in an fMRI machine, scanned their brains while they were memorizing numbers and people's faces and pictures of snowflakes, they found that the memory champions were lighting up different parts of the brain than everyone else. Of note, they were using, or they seemed to be using, a part of the brain that's involved in spatial memory and navigation. Why? And is there something that the rest of us can learn from this? The sport of competitive memorizing is driven by a kind of arms race, where every year somebody comes up with a new way to remember more stuff more quickly, and then the rest of the field has to play catch-up. This is my friend Ben Pridmore, three-time world memory champion. On his desk in front of him are 36 shuffled packs of playing cards that he is about to try to memorize in 1 hour using a technique that he invented and he alone has mastered. He used a similar technique to memorize the precise order of 4,140 random binary digits in half an hour. Yeah. And while there are a whole host of ways of remembering stuff in these competitions, everything, all of the techniques that are being used, ultimately come down to a concept that psychologists refer to as elaborative encoding. And it's well illustrated by a nifty paradox known as the Baker-Baker paradox, which goes like this. If I tell two people to remember the same word, if I say to you, remember that there is a guy named Baker, that's his name, and I say to you, remember that there is a guy who is a baker, okay? And I come back to you at some point later on, and I say, do you remember that word that I had told you a while back? Do you remember what it was? The person who is told his name is a baker is less likely to remember the same word than the person who is told his job is that he is a baker. Same word, different amount of remembering. That's weird. What's going on here? Well, the name Baker doesn't actually mean anything to you. It is entirely untethered from all of the other memories floating around in your skull, but the common noun baker, we know bakers. Bakers wear funny white hats. Bakers have flour on their hands. Bakers smell good when they come home from work. Maybe we even know a baker. And when we first hear that word, we start putting these associational hooks into it that make it easier to fish it back out at some later date. The entire art of what is going on in these memory contests, and the entire art of remembering stuff better in everyday life, is figuring out ways to transform capital B bakers into lowercase b bakers. To take information that is lacking in context, in significance, in meaning, and transform it in some way so that it becomes meaningful in the light of all of the other things that you have in your mind. Now, it is nice to be able to memorize speeches and phone numbers and shopping lists, but it's actually kind of beside the point. These are just tricks. They are tricks that work because they are based on some pretty basic principles about how our brains work. And you don't have to be building memory palaces or memorizing packs of playing cards to benefit from a little bit of insight about how your mind works. We often talk about people with great memories as though it were some sort of an innate gift, but that is not the case. Great memories are learned. At the most basic level, we remember when we pay attention. We remember when we are deeply engaged. We remember when we are able to take a piece of information, an experience, and figure out why it is meaningful to us, why it is significant, why it's colorful, when we're able to transform it in some way that it makes sense in the light of all of the other things floating around in our minds, when we're able to transform bakers into bakers. The memory palace, these memory techniques, they're just shortcuts. In fact, they're not even really shortcuts. They work because they make you work. They force a kind of depth of processing, a kind of mindfulness that most of us don't normally walk around exercising. But there actually are no shortcuts. This is how stuff is made memorable. And I think if there's one thing that I want to leave you with, it's what EP, the amnesiac who couldn't even remember that he had a memory problem, left me with, which is the notion that our lives are the sum of our memories. How much are we willing to lose from our already short lives by losing ourselves in our BlackBerries, our iPhones, by not paying attention to the human being across from us who is talking with us, by being so lazy that we're not willing to process deeply. I learned firsthand that there are incredible memory capacities latent in all of us. But if you want to live a memorable life, you have to be the kind of person who remembers to remember. Thank you.
So that was Joshua's video on feats of memory that anyone can do, and I encourage you to watch the whole version of that. I spliced part of the videos out so that we could make this lecture a bit shorter. And that's going to end the first part of our lecture. I'm going to record a couple other parts, but you'll have to watch them separately.